So we're now in the mode where we started talking about linking different equations together. And so that was always our goal in this class. Last time you'll recall we talked about dual porosity, dual permeability systems, where we can take two systems that are kind of identical to each other, this idea of overlapping continua, and through that treat each system independently to be able to solve for flow in the fractures, excluding the matrix, and in the matrix, excluding the fractures, and then come up with some way for them to talk to each other. And so the whole message there was that we can do that quite straightforwardly as long as you define the linking terms. And so that was one form in which we could do the linking. The other form, and perhaps which is more significant, and perhaps more a focus of this class, is to now start linking the individual mechanisms that we have together in terms of the different kinds of behaviors. So when we started out with this class, we were talking initially about flow behavior, so what we might call hydraulic, the H in THMC, and we ended up with some relationships that said something like, at least in the steady state, Kp is equal to flow rates. And so that may be what we'd refer to as hydraulic. We talked about advection diffusion, and we ended up with relationships that, as you may recall, that if we combined an advective and a diffusive matrix, conductance matrix, operating on concentration, we ended up balancing that with a mass flux, and that is this particular one here. And we didn't really talk much about temperature, other to note that temperature behavior would be exactly the same as this if it was a thermal flux that we're balancing, and we'd also have advective and conductive, I guess we'd call them matrices, which would be similar. And we did it backwards because, of course, the first finite element equations to be developed were those linking for the displacement method of structures. So linking magnitudes of displacement with nodal values of forces. And we also talked about Navier-Stokes. But anyway, so when we look at the kind of terminology that's applied to these, this THMC, which is quite commonly used as an abbreviation, it defines the kinds of linkings that you want to have where you're not dealing with these in isolation, but when you tie them together in some useful way to be able to solve the problems you want. And so the first coupling that we'll talk about is the one between mechanical behavior and hydraulic behavior, to link these two. Of course, we could put together these individual terms in this expression. If you wanted to, for instance, what we could do is we could just take for instance, the time derivative of this and look at how displacement rates change with forces. And if that were the case, then I guess this would be our displacement. What are we going to call it? Let's call it Ku for K displacement. This is Ku. The one that operates on permeability or hydraulic conductivity is this Kf, for that matter. And that operates on fluid pressure and gives us a flux. And there are other components which relate to the cross-couplings that we have in those systems. So it's interesting in that, first of all, our pressure and rate of change of displacements are the terms that we're going to mess around with. So those are where these two matrices arise. And the essence of understanding this coupling then is going to be figuring out what these off-diagonal components are, what the form of the coupling are. So we'll kind of approach it using that. So to explain the kinds of behaviors we have, I mean, this is typically the idea of consolidation. And so the system is one where maybe you take I think we have a picture here. And so we certainly know how to get these conductance matrices and the stiffness matrices because you've done that before. So that's not going to change. So the challenge in all of this is being able to figure out exactly what these cross-coupling terms would be. And so physically explaining that, it's appropriate to kind of look at what poromechanics or poroelastic behavior is. So this is our HM, all right, in terms of hydromechanical coupling is what we're attempting to do here. And the essence of this is that if you take a bag of marbles, which might happen to be some solid grains and some fluid, and you put a bag around it, and then you pull all the extra air out of the bag so you have a nice tight mixture of grains and fluid and only that, and you try deforming it, what you'd find is that as you try and deform it, because water is relatively incompressible, that as you deform it, you get no particular volume change because the fluid that's present in the pores doesn't allow that structure to deform in any way. And so the idea is that to be able to allow it to deform, it's like a shock absorber on a car. To allow it to deform, you have to compress the fluid, and if you really want it to deform, you have to let that fluid drain out of it in some way, in which case that fluid can go out into out of the control volume by escaping out of here, in which case only then is it free to deform. And so the coupling is in two directions. One is if you apply a load, it won't deform and something else happens. So the way to think about it is if you have a can full of water only and you apply a load on that can and allow the top to depress, the fluid pressure in the water will go up through the compressibility of the fluid. And it's only if you allow the fluid to escape that you'll get a big deformation of that. So that's the one-way coupling. You apply load, you get a fluid pressure change. The other way coupling is that if you change the fluid pressures in the system, then what that will do is it will change the effective stresses or the intergranular stresses and allow the system to compress. And so we haven't talked very much about effective stresses and total stresses in this class, but the essential component in understanding this pore mechanics is to understand that there is a concept which is effective stress, which says that the total stress that you apply to this system is equal to, in the kind of geological and geophysics literature, the sign convention is always written in this way. It's equal to an intergranular stress plus the fluid pore pressures. So in other words, if you take this system here and you apply what we'll call a total stress to it, then inside here, that will be, we can decompose that into two components. An effective stress or an intergranular stress, and also a fluid pressure. And I don't mean that these are vectors right now. They will be in some way, but I don't mean that. And also there's some parameter that multiplies them. And this parameter is called the BO coefficient. And it's basically, we think it's equal to 1 minus the stiffness of the skeleton divided by the stiffness of the grains. And so when the stiffness of the skeleton is tiny, in other words, these grains can deform next to each other, then this ends up being 1. And if the stiffness of the skeleton approaches the stiffness of the grains, then it is equal to 0. And there's no actual effective fluid pressure on modulating behavior. And so the important concept of effective stress is that when we solve problems, we define them in terms of boundary conditions, which are applied externally, which are total stresses. And so you can think of this as being the boundary condition that we apply in terms of total stresses. But when we look at behavior internally, the deformations that we get are correspond to the effective stress. And so it's the effective stress that causes the deformation. So two things. Boundary conditions are defined in terms of total stresses, and the stress equilibrium equations, even though we really haven't talked about those, are written in terms of total stresses. But interior behavior, deformation, is conditioned by effective stress, not total stress. And also failure is controlled by effective stress. And so those are the two conditions that we have to account for. And so what we will do is we will introduce this. I don't know whether we'll get through it in one session. Maybe it warrants two sessions because it's kind of an important topic in geophysics and geomechanics. The original idea of this was put down by Terzaghi in the 1930s, looking at trying to understand the consolidation of clays along the banks of the Danube, I think in Vienna at the time. But the most broadly accepted theory, when you have compressible constituents, in other words, where you might have compressible soils and also compressible fluids, is by BO, referred to as BO poroelasticity from 1941. And so what we'll do to address this is that, since we're talking about things in finite element format, is we'll kind of introduce it in finite element format, which is what we'll spend the first little time doing. But you'll see as you go through here that this original paper by BO is also in these notes, worthwhile reading, because it's actually put out very straightforwardly and matter-of-factly that you should be able to, if you wish, you should be able to work your way through it and understand exactly what's going on. We approach it a slightly different way. He does it in terms of the constituent elasticity equations and links them. We'll do it by taking what we know already about finite elements and then putting that together. But the essential components of it are, you end up at the same point by taking either of those routes. So we'll talk about BO poroelasticity. We'll remind ourselves again that we are talking about two systems that we're coupling together: a mechanical system, F equals Ku, and a flow system, Q equals Kh or Kp. And then the challenge to us is indeed figuring out exactly what these linkages would be. It helps also to think about the equations and what they represent. So before we go maybe to the derivation, we perhaps should just say that. So we know that this equation, if you recall, where did it come from? It came from virtual internal work being equal to the virtual external work, which was actually a surrogate for F equals ma. Our accelerations are 0, and so basically the idea the sum of forces have to be equal to 0. And so our equation finite element statement really is basically looking at equilibrium in x, y, and z if we have a three-dimensional system. And so the equations that we get are in functions of forces. And so the linkage that we have in this is going to be the effects of fluid pressures on those forces. And so what it will turn out to be is that the linkage is as a body force, and it's equivalent to a change in pressure with length. If you think about a change in pressure, what change in pressure is in newtons per meter squared. If you look at that pressure change over length, there's another meter term in it just by looking at the dimensions of this. And then so it's newtons per volume. So you can think of the body force that we'll end up applying as being related to the pressure gradient. And so really all it's saying is that if you have pressure that's acting on a block, and it goes from some magnitude upstream to some smaller magnitude downstream as it acts on this block, then if you look at equilibrium, the pressure on this side is 0, the pressure on this side is finite, and it's changed that pressure over some length. And so this mismatch in pressure as you go from one side to the other is a force that has to be accommodated in the system somehow. And so that's the component that we'll end up putting into we'll see it goes into the force equilibrium equations which define this. These are written in terms of a volume rate of change. So in the same way as these are forces that are applied here, or perhaps rates of changes of forces, then a volume flux is the balance that we have on here. So we're conserving volumes. And so the effect of the linkage between this is that if you apply a displacement to the structure that will act through this term here, then in the equation for flow, which is this one here, it has to affect the mass balance. And so if you squeeze it by some amount by displacing it, by straining it, you physically will push fluid out of the system. And so you're balancing fluxes. So the two systems that are linked, if you like, in a physical way, by a body force which results from the fluid pressures in the mechanical expression, and mass flux by squeezing fluid out of a sponge as you deform a sponge and squeezing it out of the control volume in the fluid flow equations. So that's kind of where we'll end up. It's always useful to keep kind of the physical interpretation of this in your mind. Okay? And so the absolute underpinning of what we're going to deal with is that we can link fluid pressures and effective stresses to total stresses. Total stresses define the boundary conditions and the equilibrium equations. Effective stresses define internal displacements and failure, which we won't talk about. And so the basic tenet of poroelasticity is to account for the Terzaghis law of effective stress. We can write that quite compactly using our matrix notation. We have, for a 2D problem, so I guess this is for 2D behavior we're dealing with here. You remember that when we had talked about solving the finite element equations, we used virtual work. We'll do that here. But first of all, we have to figure out exactly what this extra behavioral relationship is that we have to accommodate, and that is the effective stress. So we can write total stresses being equal to effective stresses plus fluid pressures. I think in these notes we won't include this alpha term, but the alpha term should be in there if we want to rigorously deal with it. It's just that it's quite often equal to 1 that we don't deal with it. If we write this out in terms of the vectors we have for a two-dimensional problem, we have stresses in x, we have normal stresses in y, and we have shear stresses in xy that define our behavior. And so the fluid pressures act only on the normal stresses. And so if we write this expression out in longhand, we have the first two are normal stresses and shear stresses, the effective versions of those, and the fluid pressures as they act only act on the normal stresses. So this term here is a 0. And so we can write this just as a matrix relationship which defines total stresses as a function of effective stresses and fluid pressures. If we had a three-dimensional problem, then there would be 6 values of stresses, 3 normal stresses, 3 shear stresses, and this matrix here would be 3 1s and 3 0s. So it'd just be different. But the only important thing to know is that we've kind of called this before shear stress. So shear stress isn't affected by fluid pressures. So what we can do is we could, now that we know what total stress, our effective stress law is, we could now go back to what I just said previously, and that is that when we look at relating strains to stresses through our constitutive matrix, so this is the D matrix that we've referred to before, then it's not total stresses that are defined by this, but effective stresses. And so you can think of it either in terms of applying a strain, and then the stresses that you develop in terms of intergranular stresses would be these magnitudes, or you could apply these intergranular stresses, and these are the strains that would result. Either way, Hooke's law is written in terms of effective stresses. So this is effective stress. And so our interest in doing that is because now what we can do is we can take this and we can put it in here. And so now we have our effective stress law written in terms of strains in our system and also fluid pressures. So this is this here. So these are total stresses. So the utility of doing that is that our boundary conditions, and indeed I suppose equilibrium, is written in terms of total stresses. Yeah, it's the same as this, right? If I wanted to look at equilibrium of this, the forces acting down on it and upwards have to be in balance. But these are total stresses that are applied. It doesn't matter what's going on in terms of fluid pressures and intergranular stresses inside there. that would condition whether it gets shorter or longer because of compression, but it wouldn't affect equilibrium. We're cutting out the system to be able to look at that. And so now that we have our effective stress law written in terms of strains, then we realize that our virtual work statement is also written in terms of total stresses. So, I mean, it's not written very well, but I'll blow that up so you can actually see it. If you remember when we developed the finite element equations for solid mechanics, we equated internal virtual work and external virtual work. External virtual work was forces times displacements. Internal work was strains times total stresses. The magnitudes of the strains we could write by this, because epsilon is equal to AU, which is this. And stresses are total stresses here. And the ultimate expression that we ended up with, whoops, get rid of this, is basically A transpose times total stresses is equal to forces, which is exactly what this expression is. So this expression we used, but we have derived it also. So forces to be in equilibrium have to satisfy total stresses in the system multiplied through by the derivatives of the shape functions. It's what we've called as lowercase at before. And so if we take this expression now, can't draw it very well, and plunk it in here, then we have this being able to define our system. So in other words, take the effective stress law written in terms of strains, put in the equilibrium equation, which is really what this is here. This is just an equilibrium equation. And then once we do that and do the substitutions, we have equation 6. And so how does that work out? So we throw this in. So we have this term here. So it'd be A transposed times Hooke's law. So this is actually be a matrix, right? Times strain. So A transposed times Hooke's law times strain. Why does it keep wanting to move? So this last term here is strain, but we can write changes in strain as a function of the derivatives of the shape functions times u and take the u outside. So this is this here. The other component we have in that goes in for stress is A transposed times m times dp, A transposed m dp. And so now we have an equilibrium equation which includes now both the fluid pressure. It did have the strain in here, but we can swap the strain out for displacements, which are one of our primary variables. And all we need to do is also realize, I suppose, is that fluid pressures are equal to the shape functions multiplied by the nodal magnitudes of those fluid pressures. If we look at changes in those, then we can just pre-multiply them by changes. And so if we switch that out, and so that's basically what this expression is, then we end up with a relationship which is this. It's equal to something that we've seen before. This A transpose dA is what we've had before, right? This has been A transpose dA. I've written it in uppercase A to make the distinction because these are the ones that are for the strain displacement equation. So epsilon equals AU. So there's a reason for writing it as an uppercase A. It's because it relates the strains and displacements to each other. And once we make the substitution, we have pressure included here. And then all I've done is just take the derivative of each of those terms by just looking at time rate of change. So in other words, ddt it. Look at rate of change in time. And that's what this expression results from. And so if you want to boil it down to something that's a bit more concrete, we have a term here which operates on displacements. We have a term here that operates on fluid pressures, and a term here that operates on forces. Instead of being displacements and forces, they're rates of changes of each of these, and these are rates of changes of fluid pressures. And so these individual matrices which link these are just made up like this. If we want to backtrack a little bit, we realize that this equation on the left-hand side is our second order of displacement with respect to x, which is the equilibrium equation with the strain displacement equations in it, kind of the Navier equation as a function of d2u dx squared in this. And this actually looks a little bit familiar to us as well. If you remember, we have also seen a matrix that looks like, what does it look like? It looks like, let me do it in the terminology we've used. Our relationship which defined advective flow was something like integral A transposed times velocity times shape function, or the other way around, I can't remember which, over the volume. And that's exactly what you have here. And this was indicative of a first order. It was change in concentration with length, right, in our case, which in this case would be the same as change in pressure with length. And so this expression here is that behavior that we talked about, that is this linkage between the mechanical and the flow behavior, in that we represent the linkage as a body force. The body force is equivalent, body force per unit volume is a pressure gradient, as we said here. And so this term here is exactly the form of that linkage that we have in that expression. So that's the first expression that we need to be able to deal with. So we have something that allows us to be able to link displacements and a stiffness matrix through to forces. Of course, you could surmise that this is exactly the same matrix as before for solid mechanics. And so if fluid pressures were 0 here, then we just have F equals Ku. This would be K, this would be U, and this would be F. And that would be exactly our system. If we want to be able to accommodate this extra term of fluid pressure, then we have to accommodate it in some way. All right? So that's the easiest way I can get to that final point in terms of the expression. And so if you also zoom back up to here, so what this would look like, then this is going to be the stiffness matrix. This is going to be this matrix, which is integral A transposed M B dV, which operates on rates of changes of fluid pressure in time. Okay. So anyway, so that's the first expression. So the first expression is a statement of equilibrium, and therefore we have however many degrees of freedom we would need to be able to represent that. We can explore that later. So now the next part is to look at Darcy's law. And so we can also kind of rederive that in the same way as we did for the Galerkin, but let's not do that. Let's do it kind of this heuristic approach. We know that Darcy's law, if we write it out, we can get a velocity is equal to Darcy's law K over mu times the derivative of pressure. So if you prefer writing things just as individual components, velocity in the x direction is equal to minus K over mu dp dx. We'll ignore the gravity term, which is this term. Let's not worry about that. Let's throw it away. If you write it for each of these components in 2 dimensions, we have x and y components, then we can write it in this form here. We did talk about conservation equations. The conservation equation, if you write this out in longhand, is going to be something like d dx, d dy, vx, vy, which if you write that out is just rate of change of velocity in the x direction with x plus rate of change of velocity in the y direction with y equals to 0. You remember it was this idea that we said that if you take a little square and you pull this piece of square with some velocity vx here, then by definition this top part has to come down at some velocity so you conserve the area of this thing. So this expression here is just saying that if you pull it out in some direction in the x direction, the top has to come down for it to be fully conserved. And so in other words, the statement of that, I suppose, is that the fluid volume that comes out of here. If you want to have no volume change, incompressible flow, then you have to have the same change in volume of the control volume, or the same amount of fluid has to come through the top. So this is a conservation of mass, actually conservation of volume, I guess, as it's written. This, if we multiplied everything by density, it would be conservation of mass. And so we have two sources by which we can change that, and they operate in the opposite direction from each other. So physically, that is, if volume in doesn't equal volume out, then that expression doesn't equal 0. And there are two ways in which that can not occur. The first term is if you take the control volume and you strain it, you squeeze it, and you don't allow any fluid pressure to rise in that system because it's open, the amount of volume of fluid that has to come out is the change in volume of that system. And so, in other words, the change in volume of that system is just going to be, well, if we write it out, the volume strain is equal to 1, 1, 0 multiplied by strain in X, strain in Y, shear strain, which is the same as strain in the X direction plus strain in the Y direction. So that's what this term is. If you change these to rates, then you can do that just as easily. And so physically what it means is it's just conservation. So if you squeeze it, you change the size of it by straining it, then that certain amount of volume has to come out, and there's no change in fluid pressure that occurs with that. So displacement changes, the other dependent variable doesn't change because there's no fluid pressure change. The opposite is if you close the boundary of the system and you try and, well, no, actually you don't have to do that. No, keep the boundary of the system open and now change the fluid pressure. So if you have a can full of something and you change the fluid pressure, if you increase the fluid pressure, then the volume of the fluid decreases, so it gets smaller inside the can. The can stays to be the same volume, and so you have to supply some fluid into it to be able to fill up that extra space that you're making. And so the volume of that change due to the fluid straining would be the pressure change in the fluid multiplied by 1 over the stiffness, which is the compressibility. So pressure change times compressibility, and multiplied by the amount of fluid volume you have in the system. The fluid volume you have per unit volume is just the volume times the porosity. And so that's where this term comes in. And so that's the other thing. So you squeeze it by deforming it. The amount of fluid that has to go outside the new contours of that boundary is the volume strain times the volume. And if you alternatively just change the fluid pressure and don't allow the boundaries to change, this is the amount of makeup fluid you have to supply to be able to keep them the same. So this acts with a positive component because you're squeezing it with positive strain and the fluid goes out. The other one is negative because you're keeping the volume of the thing closed, you're changing the fluid pressure, fluid shrinking, so to be able to keep that volume filled, you have to add water to it. So they occur with different signs. And so this is just the statement of continuity that we'll use. So if you want to think of it in terms of language, volume in equals volume out plus changes due to straining of the system and changes due to compression of the fluid in the system. If you take Darcy's law, bless you, and put it in here, then you end up with this expression here after you rearrange it. So Darcy's law is just this term here that we've just added. Let's ignore this, unit weight. And then I guess if we don't want to go to derive the Galerkin expressions, then we need to think about what we have. So this is our normal second order PDE. So this is written in terms of d2p dx squared, etc. multiplied by permeability and viscosity. So this is this here. Well, I guess that's here. This is the other terms written out in longhand, and this is the effect of fluid strain. So these are just the uniform fluid pressure within the system. Of course, it will be mapped by the shape functions, but if we're taking just a control volume for now, we don't have to worry about this. and these would be the strains in the x and y direction system. So this is just 13, I guess, is equation 12, just written out in longhand. And so now we know we can do this heuristics that we've done before to figure out exactly what the finite element equations would be. So this is our pressure diffusion equation, second order in space, 0th order in time. And we know that if we do something with that, it will look like, maybe it's worthwhile just skipping this step. I don't think we need this step, right? It's going to look like this. This is that term. A transposed Ka, this is our Darcy's law. This is the fluid pressure after we've made those substitutions. So we've done that before. You'll note also that I'm using lowercase a because, what is it? The pressure at any particular point is equal to, the pressure at any point is equal to the shape functions multiplied through by the nodal pressure, and also the gradient of pressure is equal to AP. So these are the derivatives of the shape functions that we use. But importantly, it's important to notice or note that it's not the same as this, right? Slightly different relationship. Same kind of thing. Change in displacement in the x direction is related to A times displacements, but it's a slightly different matrix. This is what? This is rows and columns. So this is 3 by 6, and the other one's 2 by 3. You'll remember. Oops. It has to be 2 by 3 for a triangular element. That is. This is for a triangular element. Okay. So don't close it. I'm not sure why that comes up anyway. So what's next? So this is second order. What is this? This is 0 in space, but first order in time. So 0th order in space is going to be, actually we can't quite do it, can we? Because it's actually first order in space, so it's not 0th order, right? Epsilon x is equal to change in displacement with location, so it's actually not 0th order, it's first order in space. And so first order in space, as we know, is shape functions, this matrix, and A. I guess we probably need to work from, it's probably easier to work from this, right? We have this term here that defines the strain due to the nodal displacements, and we're pre-multiplying that by this weighting function, which in this Galerkin method we just put equal to the shape functions, B transpose. And so this B transpose comes exactly from there. This displacement rate here we get merely by substituting, this strain we get just by substituting the strain displacement relationships. And so we end up with this term here, operating on rate of change of displacement. And this term here is also just a pressure change. And so from this we know that this is 0th order in space, and I guess first order in time. We don't care about the first order in time, but 0th order in space is just going to be B transpose B times this term here. And so this is just this individual component. And so we have a component which is our normal conductance matrix and two linking terms. The first term is due to the fact that we can get compressibility of the fluid will give us some effect. And the second is that if we strain the porous medium, there's a certain amount of fluid that will get squeezed out. This whole equation is written in terms of fluxes, volumes per unit volumes if you like. And so if you squeeze with a displacement or with a strain, you end up squeezing a certain amount of fluid out of the system, depending on the rate at which you're straining it. And so if We write that out in longer hand, where we know that we can get the A matrix somehow. We've done that for flow problems. This A matrix would be this. And I suppose it's worthwhile noting, right, that the relationship which links strains and displacements is this uppercase A matrix. So this isn't a mistake. This is this uppercase matrix here. And so if we know what these individual terms are, this is just going to be our Darcy's law. Fluid pressure, gradient of pressure matrix in this case, shape functions, and the strain displacement matrix in this case. So perhaps it's worthwhile stepping back and realizing that we have something which relates to fluid pressure and something which relates to flux. So if we write them out using all of these components, we have a portion that relates to fluid pressure, which we'll call this. A portion is equivalent to nodal fluxes, and we have parts which are relate to the mass, the rate of change of strain, and the rate of change of fluid pressure, which are just individual matrices that get added to this. And so, again, if we make life easy for ourselves and assume that there are no effects of poroelasticity, then both of these expressions here will disappear, right? No strains, no pressures, but you're only looking at the flow equations, then this is just our normal expression that does this. This is our flow rates, and we don't think about these terms. Since all of the components in this equation have to be apples, adding apples to apples and oranges to oranges, so the apples would be flow rates, and these, you could think of these as flow rates per unit volume, or volume rate changes per unit volume. This is the volume rate change you get if you squeeze it in deformation and allow that fluid to escape. This is the volume rate change you get if you change the fluid pressure and allow the fluid to compress and then supply a catch-up volume by kicking stuff into it. So those are the basic relationships. And so, as I said, the key really is being able to figure out exactly what the magnitudes of these cross-coupling terms are. It's kind of messy here, and I can't go back to it particularly, but you'll see that the solid matrix, solid equation has normal F equals KU in it, but a coupling term, and this coupling term is a body force. The flow matrix has a term which relates to normal Darcy flow through nodal values of fluid pressures linked to flow rates. And if we want to be able to link pore mechanics in properly, we have to have these two coupling terms. One of these coupling terms acts on displacements and is the volume change that occurs as you strain it and push fluid out. The second one of these operates on fluid pressure changes and relates to the volume of fluid you have to add to the system. If you increase the pressure of the fluid shrinks, leaves a headspace, and you have to fill up that headspace. So in terms of physical explanation, I think that's kind of what's going on. So it is a complicated system, but I reiterate that really what we've really just done today is to kind of figure out what these three linking matrices are. Okay. Everyone okay? All right. So what do we have? We have this, which represents conservation of volume or conservation of mass. We have this, which represents force equilibrium, operating on displacement and pressures, operating on displacements and pressures, and also straight pressures rather than pressure rates. And if we put those together, we end up with this expression. It's just the same expression we had on the other page, but it's written without concentrations and temperatures for the other two equations to mess things up. So let's take stock again. If we're just looking at solid mechanics, this is our best friend. This is our stiffness matrix. If we're just looking, and you see that because this is a displacement rate, this has to be a force rate. But this then would be, since we just differentiated with respect to time, then this equation hasn't changed. The two dependent components have changed. Rates of change of displacements, rates of change of forces. If we're just solving the flow equation, then this is our conductance matrix operating on fluid pressure and a flow rate. A flow rate is already a volume per unit time, so it's kind of in the same units as this. So just by definition, we haven't needed to change that. And so that's what we had before. So now what we've done today is we've figured out what this component here is. This, we said, is really a body force, which gets added into this equilibrium equation. And depending on how the magnitude of pressures are and how they vary in space, then that defines this. This term here operates on displacements. So this is the fluid out due to strain. And if you like, this is fluid in due to delta V fluid due to delta P, changing pressure. So you change the pressure in the fluid, you change the volume in the fluid, you have to make up that volume from the surrounding elements to be able to keep continuity. So those are the individual components. We can write them at any particular time that we want, tau, if we want to solve them. And I guess the other interesting thing is if you look at these two relationships, B12 and B21, I don't think I can get them on here at the same time, but this is A transposed MB dx dy, and the other one is the opposite, A, M, B. They're the transpose of each other. So I won't derive it, but you can see that actually it's a symmetric matrix. So these two are the transpose of each other, and as a result of that, the matrix, kind of surprisingly I think, is a symmetric matrix equation still. All the terms in the stiffness matrix are symmetric. All the terms in the conductance matrix are symmetric. These are symmetric because this is just B transpose B, and if these two off-diagonal terms are the transpose of each other, then the whole system remains symmetric, which is kind of interesting. So what do we do to solve it? Well, I won't belabor the point, but to solve it, what we can do is we can figure out how to get rates of changes of displacement, which are just d dt of u, which we've done it before, right? We've done it for heads, but there's no reason why you couldn't write this for displacements and time. And that is, we have some displacement at some time. We have another displacement at a different time, which is, what's this? T plus delta t. Oops. We link those through by some curve. This is u t plus delta t. And this, the slope of this curve is exactly this, right? Just by doing the differencing. And so if we take the magnitudes of rates of change of displacements, rates of change of fluid pressures, just like we did for dual porosity, dual permeability systems last time we met, and we substitute in for this, then we can rearrange the terms to get all the terms at t plus delta t on one side of the equation, which we want to solve for, and all the terms for the previous time step, which we know, on the other side of the equation, which we don't need to solve for. And so if we substitute these two expressions into here, and just to rearrange, we end up with this final matrix relationship. So it looks kind of complicated, but it's not particularly. It contains lots of things that we know. It contains our stiffness matrix, our body force matrix, our squeezing out fluid from the sponge by strains, changing the volume of the fluid by changing the pressure, and it contains our Darcy flow matrix, which we all know. It contains these things that we don't know that we want to solve for. We know the displacements and pressures from the previous time step, and we know all of these physical matrices depending on our choice of element. And we prescribe some boundary conditions in terms of forces and stresses, and we solve it as a system of equations. So that's really all it is. And so that's basically our way of dealing with it. So it's kind of complicated and involved, but the main things to realize are that we're just taking two expressions. We're realizing that initially if you solve them in COMSOL or anywhere else, they're unlinked, and you want to be able to make them talk to each other. You want them to make the displacements in the solid mechanics system talk to the fluid pressure changes in the flow problem, and you want the fluid pressures in the flow problem to be able to talk to the evolving displacements in the element. Nothing more than that. Depending how you think about these systems, so certainly that's one way to do it. So we have the matrix equations defined by this heuristics that we've done here. And so really what we've done is we've incorporated effective stress. If you think differently and want it in a more compact way, then BO's equations are here for you to be able to do. But let's just kind of also go through it in 5 minutes in exactly the way that BO first derived these. It may be simpler because it's much more compact. It all fits on this one page. And so if you look at it in terms of continuum mechanics solution, then the equivalent of our F equals ma is the equilibrium equation. It says that rates of change of stresses, normal stresses, shear stresses, body forces, and of course this is equal to ma, right? This term here, this is the inertial term, are equal to 0 if this term is also equal to 0. And so what you could do is, the normal way of solving solid mechanics problems is to take some definition of what stresses are and substitute it into this equilibrium equation. So we made the point before that if you solve it, the reason that finite element codes all look the same and can solve flow problems and transport problems and mechanics problems is that they all do these four things together. They have a conservation equation, conservation of momentum for solid mechanics, or Navier-Stokes, conservation of mass for Darcy flow, fluid mass, conservation of solute mass for Fickian diffusion, or conservation of energy for thermal problems. So, conservation equation. They have a continuity relationship. Continuity says that as you go through the system, all the dependent variables are continuous. So as you go from one point to another point in your physical system, displacements are continuous. They don't have jumps in them. Fluid pressures are continuous. Concentrations are continuous, or temperatures are continuous for the four classes of problems. So conservation equation, continuity equation, constitutive equation. They also have to satisfy constitutive equations. So solid mechanics, Hooke's law, fluid flow, Darcy's law, diffusion problems is Fick's law, and also advection. And thermal problems is Fourier's law. Heat fluxes are proportional to gradients of temperatures. So conservation equation, continuity equation, dependent variables remain continuous, constitutive equation that links two variables, stresses and strains, fluid pressures and fluxes, and then finally boundary conditions and initial conditions. So that's the path for a normal solution. So conservation of momentum is this expression here, F equals ma. Continuity means that we don't actually we actually satisfy it automatically, so we don't actually need to be able to show that displacements are continuous and therefore strains are always finite, but that's really what continuity says. So continuity defines that strains are related by displacement gradients or shear displacement gradients, but also in the fluid phase that changes in the fluid volume per unit volume are the fluid strains. So these are fluid strains. So conservation of momentum, strain displacement relationships or continuity, and then our constitutive relationships. We defined our constitutive relationships in terms of maybe, I don't know whether you want to call them the Ford relationships, which relate strains to stresses, but now also to fluid pressures. This is effective stress wall. You can also write these back the other way. So you remember when we talked about solving two-dimensional problems or one-dimensional problems, we had to constrain them in some way by doing plane strain or plane stress, etc. So we manipulated them. We manipulated them to be able to satisfy that condition, but we also then switched them over to be able to define not strains as a function of stresses, but also stresses as a function of strains. So these are the reverse relationships. So if you can relate the relationships on the right-hand side, not in this way, but transform in this way, it takes a bit of algebra, but you can get there. And then you have something immediately that you can substitute into this expression here. So this is the constitutive relationship. It includes the effect of fluid pressure because strains and total stresses are linked, including fluid pressures, right? So effective stresses define strains. And so actually this is exactly what we did in the finite element equations, if you remember. It's the very first equation. This. Basically this, right? We wrote it slightly differently. But if you write it out discretely, then it's written as in this particular form here. And if you now throw this into this, you get what's referred to as Navier's equation to be able to combine equilibrium and the constitutive relationship together. And the resulting expression ends up looking something like this. Won't go through the derivation, but this is what it looks like. It wants to jump around. So merely if you take equation 2.11, I guess these numbers here, by the way, refer to the numbers in Bio's paper. So this is actually just an explanation of Bio's paper. So if you substitute 211 into 1.2, you end up with this expression here, which I don't know what it is in Bio's paper. So displacements, this is just one of the equations for displacements in the x direction, strains, and fluid pressures. If you go back to what we've done, actually, do we have both of those components? Why do we? Oh yeah, okay. So that we have displacements. So this one includes both the normal strains and also the volume strains and fluid pressures. Yeah, so it doesn't quite work out quite the same, but it's fine. It doesn't matter. Okay. So we've got those components. And then if we take the continuity equation says that volume in equals volume out. If that's not true, then there has to be some volume strain of the fluid in the system. And that volume strain of the fluid can come from two sources. It can come from the fact that we compress the porous medium and squeeze some fluid out, in which case this is the amount that's here. Or we can change the fluid pressure in the medium, and as a result of that the fluid compresses and you have to make up that volume with some other fluid that comes into it. And so if you take this, you end up with this relationship here. And again, the Darcian behavior. When we've talked about porous media flows, then basically what we've done is we've taken these two terms together. This 1 over Q is kind of a storage matrix, right? We've written these things typically as K del squared H is equal to specific storage times H dot. And so the heads for pressures, so this is some kind of storage term in hydrology, or 1 over Q is just one of the Biot coefficients. And so as a result of that, certainly when we solve flow equations without this strain term, we can do that without having any other information other than just fluid pressures. And usually the assumption in groundwater hydrology is that total stresses don't change. And so if you have a packet of stuff and you change the fluid pressure in that packet, then the only thing that happens is you get compression of that packet due to the same total stress that acts down. You're not modifying those stresses as you go through it. Poroelasticity allows you to be able to do that. Right. Okay, so the reason for kind of throwing away all that we've done to be able to now use these equations is to figure out how we might do this in COMSOL. And so if you take the fact that we have one equation that satisfies this Navier equation, which satisfies conservation momentum and the constituent relationship, then the only thing that we need to change is going to be to have a term on here that represents the body forces. Some term that looks like a coefficient between 0 and 1 times pressure gradient. This is all we need. So to add something, and this is actually equal to a body force. In other words, if you go back here, it's equivalent to this body force. So another body force would just be self-weight, right? If you include that in your simulation. We haven't really talked about self-weights in our simulations. So that's the one term that we need to add to the solid equation. For the flow equation, we have everything we need, everything in terms of flow, fluid pressures. So you have an extra term, which is equal to alpha times rate of change of volume strains, not strains in the x direction, with relate to time. And so if we want to be able to solve the problem, then all we need to do is be able to add in those two components. Okay. Let's see if we have time to do this. Okay, let's see if this is going to work for us today. Oh, fantastic. Let's see if this works. Oh. Is my programmer here today? No, my programmer's not here today. I think it's going to work for us. It's just thinking. So what we'd want to do is to be able to put solid mechanics relationship into COMSOL, put a flow relationship into it. I don't know whether I can do it in the time available, so what I will do is I will go to something we have to make the demonstration. Still has. Oh my goodness. What's it doing? That's interesting. Why didn't it do that? Okay, didn't. Perhaps we'll have no choice but to do that. So let's try again. Ran before, I thought. So FL is FemLab. So let's see if it wants to run. Okay, doesn't want to do it. All right, let's do it by hand. All right, so what would we do? We've got no multiphysics in there, so we go back here. So what we would want to do, I suppose, is we're not going to take the easy way out. We could just do it from scratch here. But we could do it by, we're going to do a two-dimensional problem. We're going to do plane strain. We're going to do static analysis. We're going to add it. Haven't put it. I guess I don't think we have a geometry in there yet. We're going to do. I like to use convection diffusion equation or diffusion equation because that's exactly what it is. I think we'd want it to be transient, and we can add that. And we're going to do this. All right. I'm going to make a geometry. I'll make our obligatory 1 by 1 by 1 square. It's very slow, so it doesn't like to do it. thinking in its own sweet time, I think. So that just expands it to the kind of screen size. Well, let's let it do that in the background. Let's return to our expressions. So what are we going to do? What we'd like to do in this expression is for the body force, we like a term which is this coefficient multiplied by dp dt. So what we're doing is we're using the diffusion equation. So these are defined in terms of concentrations. And so we will come back to this. Yeah, it's just very slow. All right, so what are we going to do? So we have both of these modules in here. If it decides to actually cooperate at any particular rate. Hope none of you are downloading big files. I'm not sure it's affecting the bandwidth or not. Maybe it's just too painfully slow to do it. Doesn't seem to be. Let's try it. Let's see if it'll. Not taking any of these commands, just. Can't actually tell whether it's hung or not. I think it's just very, very slow. Then it decides to do everything all at once, of course. Oh, God. So it's, well, we might not get much joy from this. I'm not sure whether, I don't have two of these things opened up at the same time, I don't think. I don't think it'll even let me do that. If I kill it. Don't know actually if that logs me out or not. See if it does any better. I don't actually hold much. So what do we want to do? We want to get a couple of modules going. We want structural mechanics, plane strain, static, because all the dynamics will be in the flow equation. And so we can add that. We want to do diffusion, we want to do transient, and we want to add that. We're going to see if it's any faster now. If we make a shape, I guess we probably don't spend too much time wondering about what that shape is, since it might hang anyway. Doesn't seem much faster. No, it's a bit hopeless. Yeah, it won't. Just too slow. It seems like it wants to show me what's in multiphysics, but it can't for some reason. You can never tell if touching something else actually helps you or hurts you. It's locked now. So anyway. Maybe I'll try recording something later. I think it's gonna work now. So, well, is there anything else that I need to say? I guess if we look at this, well, I mean, I think the linkage. So this one-page deal is actually quite useful because it just approaches it in a different way. And so some of you maybe are used to thinking of things this way. So you can do it either the heuristic way, which we did for the finite element equations, or you can do it this way for the differential equations for poroelasticity. But either way, you end up with a system of equations that, for our case, in COMSOL, the first part takes care of this, and what we have to add is this additional component here, which is basically a body force. And the flow equations, the part that's taking care of the diffusion equation is the steady part and the transient part. And we have to add a term that represents this. And there's actually a fair amount of symmetry, if you think, in terms of these terms. So this term here is alpha times alpha times rate of change in displacement in direction times displacement in time. And this term here ends up being alpha times rate of change in space times change in pressure with time. So the terms are identical to each other. The only thing that differs is the magnitude of the dependent variable that we're operating on. So this is written in terms of displacements, but we write the equations in terms of displacement rates. And so this pressure term goes into being a rate of change of pressure given by this. And so these terms that we add first to the solid equation is pressure change, rate of pressure change in space, and the term that we add into the flow equation is a rate of change of displacement in space. And the rate of change in displacement, of course, you could also write as being the same as alpha times rate of change in time of strain in the x direction. It's not just the x direction, it's actually volume strain. But you get the basic idea. So the coupling terms between these two are basically the same. So I don't know whether this has done anything. Oh yeah. So what we would, yes, it's going to be too slow. So what we'd like to do in this first expression here for the solid mechanics equations is we'd like to have a term that would represent alpha BO times pressure changes in space and time. And so the actual component would be, I think, the way that COMSOL does this is it has a concentration, which it defines as this variable. If it has a concentration with x, this is the same as rate of change of concentration with x. And so this expression here would be applying a body force, and that body force would be equal to alpha BO times, what would it be? It would be the derivative of something like concentration with x differentiated with respect to time. So it'd have some expression like this. Would be the high-level command, if you like, for COMSOL to make it do that. So yes, it's just too slow. So not worth it. I'm going to leave it there. So the other thing you could do that you might be interested in doing is take. I just started doing it today, so I was partly interested in that. Was taking EGE-FEM and make the expressions work for poroelasticity. It's really quite a straightforward modification, I think. I didn't finish it yet. I spent an hour or so doing it this morning. But I think it'd be an interesting thing to do, which is just a different way of approaching it, which allows us to use the equations that we developed for FEM. So there's two ways you can do it. You can either do it from the basic finite element equations to be able to figure out what the matrices are, then implement that somehow in your own code and understand that. The other way is to do it in this higher level way of trying to make COMSOL do it. And just to reiterate, basically all we're doing is in the solid mechanics equations, we're applying a body force. And so that's kind of apparent here, is that in these equations, this term here is just a body force that's being applied to represent this behavior here. And in the flow equations, we're representing a term that allows us to be able to squeeze fluid out of it to represent the fact that displacements will cause this change in the continuity relation, mass conservation equations. And really that's ultimately what it is. And so the theme when we go through any of these things, when we talk about coupling, is we know what the individual equations are. Solid mechanics, flow, thermal transport, mass transport. They all exist on the leading diagonal only. If you want to be able to link them in some significant way, you just have to figure out what the interactions, how those things talk to each other. And that's what we've been trying to do here. So I'll leave it there. I apologize about COMSOL, but